All right, section 9.2 is multistage experiments, and it really is just a continuation of the first section, right? The difference is instead of just doing one event, we're going to do an event that has multiple steps. So maybe instead of flipping the coin one time, we flip the coin 2 times. Instead of rolling the die one time, we roll it 2 times. Those kind of events, okay? So starting with this, we're going to talk about what a tree diagram looks like. And they actually talk briefly about tree diagrams in section 1 in your book. 9.1, but it's really not all that helpful when you really just have a one event happening, okay? But when you have multiple events and multi-stage event happening or experiment happening, it becomes much more interesting. So this is just a sample space model where each outcome is designated by a separate branch. When you have a one-stage experiment that is over, it is over after one step. So let's do the experiment, for example, where we roll a 6-sided die. So if I do that, what I do is I start with, in fact, you know what, let me put it down below. You guys can do yours out to the side. I'll have more space to work. So this is my first one picture. My 2-stage experiment picture I'll draw next to it. All right, so what I do is I draw a node, or a dot, okay? And then that dot represents sort of my starting spot. And then what can happen next is going to be represented by branches. Because there are 6 different things that can happen when I roll my die, I have 6 branches. Okay. If I'm wanting to draw a complete tree diagram. And those 6 branches, what I write at the end of them is the outcome. So what is one possible outcome when I roll a die? A 2. I'm going to put them in order though. I can also have a 1, a 3, 4, 5, or 6. These are all the possible outcomes. Or if I were to create a sample space, it would have these 6 items in the sample space. Okay, one-stage experiment. Okay, here's one other thing that happens on a tree diagram, and I'll change colors just so that it's more visible, is we put the probability of each branch along the branch. So what is the probability that I throw or roll a 1? 1/6. And a 2? 1/6. And a 3? Yeah, they're all 1/6. This is not a very diverse graph. Some of them will be. This one isn't. They just are all 1/6. And this is the complete tree diagram for a one-stage experiment of rolling one die. Sound good? Okay. So a 2-stage experiment would be, for instance, you can think of it as rolling 2 die, or rolling a die and then rolling the die a second time. It's the same thing. So if I roll 2 die, or if I roll 1 die twice, it's the same thing. So we're going to draw a tree diagram for that one now. So here's my example. And we're going to roll a die twice. That's how I'll word it. Now we start with the same kind of picture that we did before. We start with the die being able to be rolled, and the first die that's rolled, or the die that's rolled first, or whatever, has 6 options. I could get a 1, a 2, a 3, a 4, a 5, or a 6. Those are the 6 different things that can happen. And then your diagram is about to explode. All right? Because if I roll 1, and then I roll my die a second time, what options could happen? All those same 6 options. And it doesn't matter whether I rolled a 1 first or a 5 first, they still all 6 can happen. So after this 1, I need 6 more lines. And after the 2, I need 6 more lines. And after the 3, I need 6 more lines. And I hope you have more space than I do. And after the 4, I need 6 more lines. I think there's one missing. And then here's my 6 down here at the bottom. Completely not drawn well. At the end of each one of those should be the numbers 1 through 6. As as you can see, this is not something that I want to draw or wanted to draw out if I had 20 options the first time and 20 options the second time. This would be use a lot of paper, let's say it that way, and probably not be the most effective use of my time. Now, mine is almost too small to do this, but hopefully yours is a little bit better. We should have 1/6 on every single branch. Okay? All of the original first 6 and all of the 6 that are off of those all have a 1/6 chance of happening. I'll draw in the one down here for 6, and I'll leave it to you to fill in the other pieces. But there should be a 1/6 here, and then each of these individual branches has a 1/6 on it. Let's see if I find the next slide. Yeah. Okay, so the next slide I'm going to just flip to real quick, and I'll come back here though. The next slide actually tells us that there's a multiplication rule in tree diagrams. If you have a multi-stage experiment and the probability of an outcome along any path is actually the multiplication of those individual probabilities. So for instance, over here, if I want to know the probability of rolling a 6 the first time and a 6 the second time, I can multiply this 1/6 times this 1/6, and it would be a 1/36 probability of that happening. Okay. Now, that's a little tricky because it depends what you're wanting to happen, right? Do you want a 6 and then a 6? Well, there's only one way that can happen. But what if you care only that you rolled a 4 and a 2? Well, if I want a 4 and a 2, I could have rolled a 4 and then a 2, or a 2 and then a 4. So it depends on how the problem's worded as to what you're really capturing in the essence of the answer, right? If you care only about what the numbers are when they're rolled, it's different than if you care about the order in which you rolled them. So be careful about the way the problems are worded. We'll see some along the way. Now, here's a note. It's in bright red, so you cannot possibly miss it. I hope you don't possibly miss it. This one tells you that I expect you to draw tree diagrams. I fully understand that there are ways to do this without tree diagrams. I get it, all right? But if you were working with children on this concept, you would be using tree diagrams. So I want to make sure that you understand how to look at it from that perspective, because that is the perspective that you would be using. Okay? All right, independent events. Independent events are events where it doesn't matter whether the first one occurs or not. It has no bearing on whether the second one occurs. Okay? So that actually happens when I roll a die, or like on a coin problem before, right? If I roll a die or if I flip a coin, it makes no difference what happened on the first flip. That doesn't affect what happens on the second flip or the second roll. Okay? The same thing can be said about certain events that happen in real life. For instance, there is absolutely no bearing on whether or not your second child is a boy or girl based on whether your first child is a boy or girl. No bearing at all. Okay? However, some events do have some correlation or some effect on one another. For instance, whether it rains today has some effect on whether it's going to rain tomorrow. Right? It doesn't mean for sure that it will or it won't, but there is a relationship between the two. One does, in fact, affect the other. Those are things that are not independent. And let me just say, independent and mutually exclusive are different things. We encountered mutually exclusive last time, so I can't flip the slide back to it because it's on in 9.1. Do you remember what mutually exclusive was? I know it's going to be. Right. So mutually exclusive, hang on. Mutually exclusive events are events that have nothing in common. That's not the same thing. Okay? Having nothing in common means that, for instance, that if I were talking about my family and my sister's family, we have no children in common. Okay, great. But that doesn't mean that we're independent of one another, right? If it's Thanksgiving, we're all showing up at my parents' house. There's a relationship there, okay? Same thing when you're looking at this, right? Independent events are events that occur without depending on one another. It does not mean that they're mutually exclusive. All right, last one here says, for any of the independent events, E1 and E2, if you want to know the probability that E1 and E2 occur, write it the same way I've got it written down here. at all. Probability of E1 and E2 occurring would be the probability of E1 multiplied by the probability of E2. Again, that only works if you're dealing with mutually or with independent events, that you can multiply their two probabilities and find the probability of both things happening. And that's in part at least why the multiplication rule of tree diagrams happens like it does, that we can multiply the probabilities individually on the branch together to get the final probability. All right, so we're going to do some examples, and that's where I think these get a little interesting. And they're not going to be as big and spread out as that 6 by 6 example, so that's the boost. An executive committee consists of 10 members, 4 women and 6 men. 3 members are selected at random to attend a meeting in Hawaii. You want to go? 2. What is the probability that all 3 selected are women? All right, so here is an example of something that's actually not not independent. And here's why. Let's go through and we imagine that we have a hat, and hat has everybody's names in it. Okay? First of all, how many names are in the hat? 10? There are 10 names in the hat. But it is not equally likely that I pull a man's name or pull a woman's name out of the hat. Why not? There's 4 women and there's 6 men. So, I'm going to start my tree diagram, and the tree diagram is going to be as though I'm pulling the first name, if you will, out of the hat. And this question actually has bearing on whether or not the people that are drawn out are male or female. So that's what I'm actually looking at. I'm looking at, did I pull out a male or did I pull out a female? So these are the 2 possible outcomes. But when I pull that name out, as you said, it is not 1/2, 1/2. Right? So we're not going to worry about reducing as we go because I want you to keep seeing something happening. How many, or what is the probability that we pull out a male's name? 6/10. And female? 4/10. Now, whether I pulled out a male or a female will affect the next draw. And here's why. The next draw is going to happen no matter what because I need 3 people to go on this trip. And again, I either get a male or a female when I draw the name. But let's take a look at the top branch. If I've pulled out a male from the hat, how many male names are currently now in the hat? There's only 5 out of 9. Because once your name's drawn, it wouldn't go back in the hat. It's not like you get to go to Hawaii 3 times, right? No. So we've got 5 out of 9 here. How many women are still in the hat? 4 out of 9. And you should notice as I'm doing these that both of those 2 numerators added the denominator. And that should make sense, right? When we're counting the number of pieces of paper in a slip, you're in a hat. Down here, however, this is not 5 9ths and 4 9ths. Because the initial draw of the female's name affected what happened. When I drew a hat from drew a female out of the hat, the next time when I draw a male, that would have a 6/9 probability of that happening, and female 3/9. Okay, is this making sense? Everybody okay with this? But I'm not done. Why not? I need 3 people to go on the trip, and so far I've only had 1 experiment right here where the first MF is, and the second experiment where the second male-female one is right here. So I need to draw it again. So on the end of each of these tree branches, I need to draw 1 more set. This will be my last set of branches. And again, each one of them have either male or female at the end of them. And you have to go through each branch and actually look at what has happened before in order to put those probabilities in. You don't just get into a default. It's not 6/10 and 4/10 anymore. In fact, how many names are still in the hat?
7 or 8.
There are 8 still in the hat, so all my denominators are going to be 8, right? And again, this is why I didn't want us to reduce the 4/10 and the 6/10 in the beginning, is because you can see this happening, right? There were 10 people originally, there's 9 people in the middle, and on each of the denominators over here, I'm going to have an 8. Okay? So I'll fill those in as we go, but all right, so top of the line, if I've drawn 2 males out of the hat, how many males are now in the hat? 4. So how many females are in the hat? 4. All right, next one out of 8. I have drawn out one male, one female. So how many males are now in the hat? 5. And how many females? 3. All right. I guess you could say the fourth set of branches. I have drawn out one male or one female and one male. So how many males are there and females? Still 3. Good. And on the last one, I have now drawn out 2 females. So how many males are still in the hat? 8. And how many females? Perfect. This is the tree diagram, filled out completely. You do not need to multiply each branch out. That's not necessary. You only need to multiply the branch if it has to do with answering the question. Okay? Now, let's actually answer the question. The question says, what is the probability that all 3 selected are women? So where is that in this picture? Yeah, it's this very bottom branch, but it isn't 2 out of 8. You see, 2 out of 8 is only the 3rd probability of that list. So what do I have to do? I need to multiply all of them. So I have 4 over 10 times 3 over 9 times 2 over 8, some of which reduce. Let's actually do some reducing before we multiply. You guys know how to do that. We've done that already. So tell me something I can reduce. 4/10 Okay. What else? I think there's one more reduce I can do. About this 2 and this 4. Right? Along the diagonals. If you don't do it now, it's okay. You'll just end up having to do it later. So this 2 would be a 1 and this 4 would be a 2. So I actually have 1s all across the top, and out of the bottom I have 30. So how likely? Not real likely.
Why is the endings on 8? Aren't we supposed to pick 3 people?
We are supposed to pick 3 people. Here we had 10 people in the hat to choose from, and then 9 in 8. Yeah? Okay, so this is not likely to happen, right? Okay. Now, what if instead of this asked this way, they said, what is the probability that at least one male gets to go on the trip? Nope. What is the probability? So I'm making up a new problem on the spot. This is what happens when you teach. You think about things. So what is the probability at least one male gets to go? Nope. You could, that still wouldn't give you the complete answer. Can't be more than 1. You say you probably is more than 1. I'm going to give you the answer, and I want you to pause for a second. Don't immediately say anything. And I want you to think about why my answer should make sense. The answer is 29 over 30. Don't say anything. I want you to think about why that should make sense before anybody talks. Everybody gets to think. Shannon, where does 29 out there come from? All of the other branches have at least one male on them, don't they? How could I get 29 out of 30 that quick though? Because you know I didn't multiply those branches together, right? Remember last time we had this formula that said the probability of A complement is 1 minus the probability of A. A complement, at least one male going, is the exact opposite of no males going. That is all females going. So if I were to take 1 minus 1/30th, I would get 29 out of 30. That's one way to do it. And a lot easier than some of the other approaches you guys were wanting to try. The other approaches would mean that I'd have to multiply every single other branch together. I need to do 7 different multiplications. and we need to add all 7 of those together. Good news is they'd all have the same denominator. The bad news is that's a lot of work, right? Okay, so this is an interesting, you'll see this happen on occasion in some of your homework too, so I wanted to draw your attention to it. All right, let's try another one. A box contains 5 slips of paper numbered 4, 6, 7, 8, or 9. The first player reaches in the box and draws out 2 slips of paper and adds them up. If the sum is even, they win. If it's odd, they lose. Okay, so we're coming back to this slide to do some work, but the questions are over here. Part A says, what is the probability the player wins? Okay. So, what we're going to do in this one is we're going to write down all of the different outcomes that can happen, but I'm kind of going to avoid a tree diagram because I don't really care if I pull a 6 and then a 4, or a 4 and then a 6. Does that make sense? I would still get 10, which is an even result, and I win. So I want to organize this a little bit differently. What I'd like to do is I'd like to say, let's say I pull out a 4, and I'd like for you to tell me what other options I could pull out with my 4. So, well, let's do 6 first just to keep them in order, and then we'll do the 7. Then what? 8 or 9. And that is all of the possible ways I can pull out a 4 and something else. Make sense? Okay. Next one, let's see. I could pull out a 6, but I don't need to list 6 plus 4. I've already listed that as an option. And the way that the event is happening is I'm reaching in, I'm grabbing 2 out at the same time. Okay. So if I pull out a 6, what else could I pull out? A 7, or a 6 and a, or a 6 and a 9. And that's it. I don't have any more options with 6. Now what? 7 plus 8 and 7 plus 9 and 8 plus 9. All right, so these are all of my possible combinations. And they all occur twice, don't they? I mean, if I were to list all of these out, really, and the order actually mattered, I'd list every single one of these twice. Except that because I'm reaching in and grabbing them out at the same time, I can't pull out, for instance, 2 4s. That's not a possibility here. So we don't see 4 plus 4 listed. So is everybody clear on that? Because if I were reaching in and pulling one out and I put the number back in, I could do that. But that's not how the problem's set up. All right. So the question then is, do we win or do we lose? So let's go through here, and I want to know which ones win. 4 and 6 win. 4 and 8 win. 6 and 8, okay. All right, so all the ones in red add up to a even number, and how many of them are there? There are 4. Out of how many? 10. Did we count 10? Did we get that? Which would reduce to 2/5. So a 2/5 probability of winning. But what if we just change the game? Instead of letting or having us add the numbers together to get my probability, we're going to multiply. So that's all we're changing. It's not a big deal, right? We're just changing this very minor detail about the whole deal. And again, the rules are the same in the sense that if it's even, I win. If it's odd, I lose. So we still want to know what's the likelihood that I get an even. So same as I did before, but I've got multiplication now. So I have 4 times 6, 4 times 7, 4 times 8, and 4 times 9. I have 6 times 7, 6 times 8, and 6 times 9. 7 times 8, 7 times 9, and 8 times 9. You should not need to multiply these out to answer which ones are even. Yeah, anything that's got a multiple or a factor, let me say it right. Anything that has a factor that's even in there will be an even multiplication, right? It's an even product. So all of these are even. All of these are even. What else? All I did was change it to multiplication. Now what's my probability of winning? 9 out of 10. So my probability of an even here is actually a 9 out of 10. Very minor change. At least it sounded like it, right? And the result result is quite different. All right, so yes, it changes the probability. Let's take a look at example 3. Got a spinner problem. We've got a spinner, and we've got 2 spinners actually, and we're going to do an experiment where we spin the first one and then we spin the second one. And what we want to do first is to find the sample space for the experiment. Now, we talked about sample space last time, and we found a couple, but the sample space is going to be listed in curly braces, just a reminder. And it's going to have every possible outcome in it. Okay? So one outcome is that I spin a 1 on my first spinner, and I'm going to write them as ordered pairs. If you want to just write them as numbers beside each other, that's fine. I'm going to write them as ordered pairs. I could spin a 1 on the first spinner, and then what happens when I do the second spinner? What would I have? I have 1, 2, or 3. So I could have a 1 and then a 1. That's an option, right? Or I could have a 1 and then a 2. Or I could have a 1 and then a 3. Okay, what else could I have? I could have spun a 2 the first time and then a 1, or a 2 and a 2, or a 2 and a 3. And I think that's all of them, right? Now you can do this with a tree diagram to think about this as well, but the tree diagram picture actually ends up looking a little different than the other 2 that we've done. So the first spinner I get a 1 or a 2. But then my second spinner events actually have 3 options, don't they? That's a little different, isn't it? Now, we do have probabilities to write in here if I think about it from this perspective. What's the probability that I spin a 1 on my first spin? 1/2. And on the second spin, or I'm sorry, and the 2 on the first spin? 1/2. Now, once I have spun my 1 or my 2 from the first spin and I go to my second spinner, what's the likelihood that I spin a 1? 1/3, because on this spinner, that is an even, or at least it should look like those are all even probabilities. How about a 2? 1/3, and a 3? 1/3. And then how about on the bottom branch? All 1/3s, just the same. So notice that this is very interesting because if you take a look at the end, this shows you exactly how many options there were. If you count them up, I've got 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. There are 6 different final options. And down here in my sample space, I listed 6 different options of what could have happened. Okay, not a coincidence. That's really what's happening. Now, there's a couple other questions about this one, so let's go to the next slide. We're going to find the probability of doing some things. That is spinning 2 even numbers, spinning at least 1, 2, and spinning exactly 1, 2. So we can either look at the sample space, or we could look at the probabilities, or the tree diagram with the probabilities in it to answer any of these questions. I think that the sample space on this one is a little bit more intuitive. And the reason it's helpful is because all of these probabilities are the same. Take a look over here and I'll show you. What is the probability of spinning a 1 and a 1? 1/6, a 1 and a 2? They're all 1/6, aren't they? And if you take a look down here, that shows up very nicely. There are 6 options and they are each one of the 6 options. So what is the probability, it asks us in the first one, of spinning 2 even numbers? Yeah, there's only one of those right here, right? 2 even numbers. So there is a 1/6 probability of spinning 2 even numbers. How about the probability of spinning at least 1, 2? How many? There are 4 of the options inside my sample space that have a 2 in them. Do you see them? 4 of them have a 2 out of how many total? And that will actually reduce to 2/3. So it's more than a 1/2 probability that will happen. The last one says exactly 1, 2. That's 3/6 because it excludes what? Excludes the roll that were, or the spins where it was a 2 and a 2. Oh, both spins were a 2. So this one actually ends up being 3/6, and that one does reduce to 1/2. Okay, we're going to do one more because it's a fun one and it's quick. promise these cannot be the right probabilities. I totally made them up. I'm sure they're much higher. When I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears it. If the shirt is stained, there is a probability of 0.2 that I will not be able to adequately eliminate the stain. What is the probability that my son's new shirt will be permanently stained the first time he wears it? This one's a little bit different. The tree diagram actually looks different. So what is the first event that happens in this argument? Whether or not he gets a stain, right? So my first node comes out being that he either gets a stain or he gets no stain. And understand this, if he gets no stain, I don't have to scrub the shirt, right? Okay, before we go on to the next branches, I want us to put in the probabilities. What's the probability he gets a stain? 0.15. And the probability he doesn't? 0.85. So another reason I want to show you this example is that you can do probabilities with decimals, right? Not repeating decimals, don't go involving those. But if you've got solid decimals, you can, terminating decimals, you can use decimals for these too. Okay, so after he wears his shirt and he stains it or he doesn't stain it, I have to wash it, right? What's the next event that happens then? Whether I get the stain out or not, right? Whether it's permanently stained or whether it comes out. But like we said, I don't have to do that at all if there's no stain. So my next set of branches only come off of the stained shirt. I don't have to do anything if it's not stained. And then we can do, I think this is how Mackenzie described it. It comes out. Or it's permanently stained. Okay, so it says, if the shirt is stained, there is a 0.2 probability that I will not be able to adequately eliminate the stain. So, what is the probability that it comes out? 0.8. And what is the probability it's permanently stained? 0.2. The question that's asked once I've created my diagram is, what is the probability that the first time my son wears a shirt it is permanently stained? Okay, so what are you using to get that? Good. So you're using this branch is what you're actually using, right, Brendan? And we can use the fact that we can multiply the two probabilities along that branch. That is the only branch where I put permanently stained shirt when I'm done. I could likewise have asked the question, what's the likelihood that he wears a clean shirt the second time? That is a shirt that's not stained the second time. I could either add up the top probability and the bottom probability. That would be fine. Or I could take the piece that's circled in green and subtract it from 1. So Brendan told me just a minute ago that if I take 0.15 and I multiply it by 0.2, I get 0.03. Does everyone else agree with that? Okay, so there is a 0.03 probability that when my son wears a shirt, he stains it the first time it's permanently stained, we don't have any more clean shirt. Okay? But on the flip side, that means there's a 97, right, 0.97 probability that it actually comes out and we're all happy we get to wear the shirt again and potentially resell it at some point because it's clean. Okay? Any questions on